that test is covering really just chapter 8. Or no, we have chapter 7 on this test as well. Is that correct? Kinematics? I'm pretty sure that's the case. 7, 8, and then this chapter 10. There'll be no chapter 9 at all. That's all to take home. Um, yeah, I lost my notes from last time. Mirror equation. Yeah. So one or two of your free response questions on your test will be something using the mirror equation or the lens equation. You'll find they work very similarly. They have the same equation basically. But this just tells us that if we have a spherical mirror, or a lens as it turns out, where we can find the image, and the mirror equation looks like this. It's 1 over the focal length is equal to 1 over the object distance, remember that's p, plus 1 over q. Need to make sure that you're okay with the algebra and solving this. Just that you're okay on the algebra solving this. And then also the signs will often get us. So let me just sort of review some of the sign stuff. Um, remember for a one lens system or one mirror, I'll just say a one mirror system, that P will always be positive. We'll see a case if we have two lenses where P can be negative, and I'll talk about that a little bit later. That if Q is negative, that's a virtual object. If Q is positive, that is a real, or not a virtual object, a virtual image or a real image. And then we'll also see that the focal length can be either positive or negative. I'm going to go ahead and tell you this now, but the focal length for concave mirrors it has a positive focal length. For convex mirrors, they have a negative focal length. All right. Um, what is the focal length for a flat mirror, by the way? Remember it's not 1, no. It's well, remember our focal length is if I have a mirror, my focal length, if this is the radius of curvature, this is the focal point or the focal length. What is that value for a flat mirror? It's not 1 or 0, but you're thinking along the right lines. Well, what happens if I make this mirror flatter? What happens to the focal point? Does it get bigger or smaller if I make it flatter? It gets bigger, right? So imagine, let me draw you say I have a mirror that's very round, and then I have a mirror that I make flatter like this. Here the focal point is going to be like there, but here the focal point is going to be moved out. Right? As you make that mirror flatter and flatter and flatter, the focal point gets bigger and bigger and bigger. So what is the focal point for a flat mirror? It's infinity, right? So for a flat mirror, the focal point will go to infinity, or the focal length will go to infinity. And I can think about this equation. If I have 1 over infinity, that's equal to 0, or it approaches 0. And then 1 over p plus 1 over q. But remember, for a flat mirror, they're equal to one another, so I can replace that q with negative p. And so this is consistent that 0 is equal to 0 for a flat mirror. All right. So it holds for flat mirrors too. We won't use it for flat mirrors because it doesn't really make sense to do so, but we'll use it for our spherical mirrors. With this chapter, guys, the problems that students often have is with the signs of the quantities that we're using. So I have a little chart here, and we'll refer back to this, but that tells you is the variable positive or negative. So for example, our object distance, if our object is in front of the mirror, which is usually the case, again, when we get to two lens systems, I'll show you where that's not the case. But if it's in front, it's going to be positive. We'll come back to this in a little bit. If the image is in front of the mirror, that means you can project it onto a screen. It's in this sort of real space. The image distance will be positive. If it's behind the mirror, like in Poltergeist, come to the light, come to the light. All right, then it's going to be negative. Y'all haven't seen that movie. I know like 3 of you have seen it. But oh, did they remake it? Okay. Does it still have that creepy lady in it? Yeah, okay. The focal length, if the focal length is in front of the mirror, it's positive. That's for a concave mirror. The focal point is in front of the mirror for a concave mirror like this. If it's behind the mirror, like with a convex mirror, then it's going to be negative. If that helps you, that's great, but we'll see sort of how those play out in some problems. I think I have a couple clicker problems here, yeah. So here, I have a concave spherical mirror. It has a radius of curvature of 20 centimeters. The object is located at 20 centimeters. What is the magnification? And just to remind you of your equations, 1 over f equals 1 over q plus 1 over p. And then my magnification is negative q over p. I'll update your equation sheet so you have those things on there. To go ahead and start that, let me pull up the clickers. Remember, your concave mirror has a positive focal length. If it was a convex mirror, it would have a negative focal length. But my concave mirror does have a positive focal length. Remember, this isn't the focal length, but you can get your focal length from the radius of curvature. That radius of curvature is the radius of the sphere from which that mirror has been cut. Oh, let me start this. What's the focal length of this mirror? It's not 20. What is it? It's 10. The focal length is half the radius of curvature. So the focal length is positive 10. What is the object distance? The object distance is 20 centimeters. So in order to find the magnification, now I also need to find Q. What is Q? We don't know Q, so you need to find Q. And then when you find Q, you can solve for the magnification. All right, I'll stop at, say, 235, 235. We're sort of all over the board here, so let's take a look and see. If I know my focal length and I know my object distance, I can find Q. I say 1 over 10 is equal to 1 over P, that's 1 over 20, plus 1 over Q. And then I have to solve this for Q. So say 1 over 10 minus 1 over 20 equals 1 over Q. 1 over 10, that's 2 over 20. So this is equal to 1 over 20. I invert both sides, and I find that Q is equal to positive 20 centimeters. What type of image is that? It's a real image. Because it's positive, this is a real image. All right, and now I also want to know the magnification. It's negative Q over P. That's negative. Q is 20 over 20, negative. And so my magnification is negative 1. So C is the right answer there. Further, I can tell some other things about this image. It's a real image. All right. Is it inverted or upright, this image? Inverted or upright? It's inverted, right? Because the magnification is negative, that tells me that it's inverted. Is this image bigger, smaller, or the same size as the object? It's the same size. So I can tell some things. First, I can tell it's inverted. Further, I can say also that it's real. We've already said this. It's real because this is positive, the image distance. And then also, because this has a value equal to 1, it's the same size as the object. So you'll have some questions on the test where you have to describe the image in words based on the image distance and then also the magnification. Let's try this next one. This is a little trickier. I have a 2 centimeter high object. It's placed 3 centimeters in front of a concave mirror. If the image is 5 centimeters high and virtual, what is the image distance? I'm going to write your equations over here. We have m is negative q over p. 1 over f equals 1 over q plus 1 over p. And then also the magnification is also hi over ho, the image height over the object height. Think about what these values, these things tell you about the orientation of the image and the signs for these various things. What is the magnification of this object? The magnification is 2.5. I know that because the image is 5 centimeters high and the object is 2 centimeters high. So the magnification is hi over ho. That's 5 over 2. It's 2.5. Now, we haven't said, is the magnification positive or negative? You need to think about that. Is it positive or negative? I'm not saying. It's either positive or negative. Uh, all right, let's try to do about 15 more seconds. Stop at 3:45. Okay, y'all doing a little better on this one. 3:45, I'll stop. I'm pretty sure B is right. Let's see. So the magnification here is positive. The reason I know it's positive is because I'm producing a virtual image. A virtual image tells me that I have a negative Q. And if I have a negative value here, that makes the magnification positive. If it was a real image, I would say that the magnification is negative. But it's a virtual image, so I know that it has to be upright. The magnification is positive because it's a virtual image. That means I have a negative Q. So M is equal to negative of a negative Q over P. So it's going to be a positive value because I know that that Q is negative. All right, so our magnification is plus 2.5. And now I'm looking for the image distance. I know that M is equal to negative Q over P. I'm looking for Q. Now I know M and P. So I say 2.5 equals negative Q over P, which is 3 centimeters. 2.5 times 3, 7.5 is 7.5. And it turns out to be negative. But negative works out here too. You find that it's a negative value. Let's try another one. You'll have questions like this in the free response portion of your next test. Here I have a convex mirror. It's mounted high on a wall to help people avoid collisions. It has a radius of curvature of 2 meters, and I want to know the magnification of a person 5 meters from the mirror. I have a convex mirror, looks like this. I have a person that's over here. You can eliminate some answers right away from this. Which ones can you eliminate for a convex mirror? Huh? The positive ones? Okay, the negative ones. Because in a convex mirror, like a security mirror, you're always upright. And so I know that the magnification has to be positive. So you could get rid of B and D here because they're both negative. If we had any greater than 1, you could have gotten rid of those two, but we don't have that. So. All right, about 15 more seconds. I'll stop at 2:45. 2:45. Just guess if you're not sure. Okay, C is pretty sure is right. Let's double check. So here, first of all, I have to find my focal length. My focal length is going to be 1 meter. It's half the radius of curvature. Um, this is my value for P. So I have 1 over 1 equals 1 over Q plus 1 over P, which is 5. That's 1 minus 0.2 is 1 over q. Actually, I'm going to keep it in fractions. So that's, sorry, 5/5 minus 1/5. That's 4/5. So q is equal to 5/4 meters. Is that what y'all got? Yeah. Oh, actually, it should not be 4/5, but what? Oh, I made a mistake somewhere. What did I do? Oh, I know what my mistake was. What's my mistake here? The focal length should be negative, right? So I should have a negative value here, and I knew it was a mistake because I know that for a convex mirror, my image distance should be negative because it's a virtual image. So let's start back here. So I have 1/5 minus 1 minus 5/5 equals 1 over q. So that's negative 4/5 equals 1 over q. So q is negative 5/4, or negative 1.25 meters. All right, so now if I want to know my magnification is negative q, it's negative 5/4, divided by p, which is 5. Yes, you're right. Thank you. So this would be 6/5, right? Sorry about that, y'all. So that's 5/6. Then I have 5/6 over 5 here. One of my 5's cancel, and I'm left with positive 1 over 6, which is the same as 0.16. All right, so a couple things we had to be aware of. The focal length is negative. Right? I made that mistake too, so have to be careful that you know the sign of your focal length. Remember, concave mirrors have a positive focal length. Convex mirrors have a negative focal length. The way I remember that, or don't remember it as it is, a concave mirror, the focal length is on the front side of the mirror. For a convex mirror, the focal length is on the back side of the mirror, sort of the virtual space. Okay? All right. We're going to see some very similar problems with lenses. I think we're going to skip ray diagrams for mirrors so that we can wrap up this chapter on Monday and then have Wednesday for review. So we'll skip ray diagrams for mirrors. There are also a few homework questions where you have to trace ray diagrams for mirrors. No, no ray diagrams for mirrors. You will have ray diagrams for lenses. They're very similar, so we'll see that on Monday, okay? So let's go on ahead to, well, shoot. Let me cover it now, but you're not going to see ray diagrams for mirrors on the test, okay? But it will be useful for you just to see them for some other questions that we'll see. The rules are going to be the same for drawing for lenses, so it's not completely useless for you to see this now. You have 4 rules for drawing rays for spherical mirrors. I said they'll be very, very similar for lenses. You draw a ray parallel to the axis. It reflects back through the focal point. Parallel to the axis, through the focal point. You draw a ray through the focal point. It reflects back parallel to the axis. And you draw a ray through the center of curvature. It reflects back on itself. I'm not going to give you the 4th rule. You really only need 2 rays to tell where an image is, because an image is going to be where the 2 rays cross. So draw one parallel to the axis. It reflects back through the focal point. Draw it through the focal point. It reflects back parallel to the axis. If you draw it through the center of curvature, it reflects back on itself. Let me show you what that looks like. For a concave mirror, the object can be in 3 different locations. You can have it outside the focal point, inside the focal point, and at the focal point. All right, if it's outside the focal point, you're going to get a real inverted image. I'll show you that. If it's inside the focal point, you get a virtual upright image, a virtual upright bigger image, and if it's at the focal point, you get no image at all. This is for a concave mirror. Let me show you. So I brought a concave. You don't usually see concave mirrors very well. They're shaving mirrors. Shaving mirrors are concave mirrors, but this is a concave mirror. Can you see yourselves in this mirror? How do you appear? You're upside down. This means that you're outside of the focal point. The focal point for this mirror is right about here or so. Means, tell us what you see when it's up real close. Right, so this is like a shaving mirror. A shaving mirror, right, makes your face really big. And so if you get really close to this, it makes your face look really big. And if you're at the focal point, you just sort of go fuzzy. Are you fuzzy yet? Yeah, so he's roughly at the focal point. He can't really see anything at all. Okay? We'll look at this in a bit longer. That's a concave mirror. Now, outside the focal point, my rays look like this. Ray number 1 is parallel to the axis and through the focal point. Ray number 2 is through the focal point and then parallel to the axis. And so my image is going to be right here. That's my image, where the 2 rays cross. And then I can go and draw ray number 3. It's through the center of curvature and then back on itself, like that. Next semester, you're going to do this in lab. You'll see it again then. So I get a image that's real, inverted, and sometimes it's bigger, sometimes it's smaller. Sometimes it's the same size. If it's at the focal point, what type of image do I get? No image at all. And you can see that here. I draw parallel to the axis. This is rule number 1, and through the focal point. And then I can draw it to the center of curvature and back again. But look, the center of curvature is behind the object. So what I'm going to do is I'm going to draw a ray that it's as if it originates from the center of curvature, goes to the mirror, and then reflects back on itself. And so this is rule number 1, and this is rule number 3. I can't draw rule number 2 because I'm at the focal point. How are those rays? Are they divergent, convergent, or parallel? They're parallel. That means they're never, ever, ever going to cross. So that means there's no image. That's a fuzzy image to us. If it's outside or inside the focal point, this is a little trickier. And again, I'm not going to have you draw these. I'm just showing them you for a reference. I draw one parallel to the axis. This is rule number 1. And then it goes through the focal point. This is number 1. Number 2 is through the focal point and parallel to the axis. So I'm going to draw a ray as if it originates from the focal point, like that, and then it goes parallel to the axis like this. So this is number 2. Now look, convergent, divergent, or parallel? These are divergent. So these are never going to cross on the real side of the mirror, but they will cross on the back side of the mirror. So I draw these, I trace these back. These are called virtual rays. And they tell me where the image is. So the image is back here. This is like when beams was magnified. So when you're inside the focal point, you always look bigger, you always look upright. It's a magnifying mirror. So this, in this orientation, this is a magnifying mirror. I can draw that third ray as well. It goes through the center of curvature and back on itself. So I would draw a ray that would go like that, and then it would trace back on itself. And then if I draw it back, it crosses where the other two cross. All right, and then for a convex mirror, again, not responsible for those ray tracings. We'll see, though, that you are responsible to know what type of images these different mirrors form, and sometimes the ray tracing helps you to remember that. If not, it's fine. We'll see ray tracing again with lenses, though. For convex mirrors, the focal point is behind the mirror, so the focal length is what, positive or negative? It's a negative focal length. Anytime the focal length is in that virtual space behind the mirror, that's a negative value. If the image distance is back there, it's a virtual image, it's a negative value. If the focal length is back there, it also has a negative value. So if the focal length is negative, think about our lens equation. 1 over f equals 1 over q plus 1 over p. If this value is negative, what does that tell us about this value? It has to be what? It has to be negative. It cannot be positive, because if I have a positive p, this has to be a negative value for any hope of this ever being negative. So it tells us that our image distance has to be negative. So that means that for a convex mirror, it's always going to produce what type of image? A virtual or real image. It always produces a virtual image. So this is a convex mirror. You see these more often. These are security mirrors, right? Post one up here so I can see all of you all at once. Right, it's a security mirror. You look smaller in it. These are upright images. Anytime you have an upright image in a mirror, that means the magnification is positive. That means the image distance is what? Because remember, magnification is negative q over p. If m is positive, q must be negative. So these are virtual images. The magnification is positive. Q must be negative. These always produce virtual images. These always produce upright images, and they always produce smaller images than the object. Okay? You need to know what types of images these different mirrors produce. And they really produce 4 different types of images, depending upon what type of mirror you're using, concave or convex, and where the object is. All right, so here we can draw those ray diagrams. These get a little trickier. I'm to sort of go through them quickly. But number 1 is parallel to the axis. This type of mirror is called a diverging mirror. That means that rays coming towards it are going to diverge in this way. But they'll diverge in such a way that if you trace them back, it'll go through the focal point. I can also draw one that's through the focal point. But I'm going to draw it like this, such that if I were to trace it forward, it would go through the focal point, and then it's going to go parallel to the axis. So this is rule number 2, and this is rule number 1. It's a little bit different. Don't sweat it right now. When we get to lenses, you'll see something similar with lenses, but don't sweat this right now because you're not going to see it again. And then I trace the reflected rays back to find out where the image is. Trace that ray back, trace this ray back, so my image is going to be right there. It's going to be an upright image. I know it's upright because the 2 rays cross above the optical axis. That's that axis down the middle through the mirror. And it's also smaller. I see that it's smaller here because the image is smaller than the object. And it's virtual. So it's back behind that mirror, so that means it's a virtual image. Know what types of images are formed by what types of mirrors and in what type of orientation. You will see very similar things for lenses. They work in a very similar way. All right. Let's try this. And actually, this was a mistake. There is no mirror that produces an image like this. Right? I cannot have a real image that's upright. That just doesn't happen. A real image is always going to be inverted. So let's instead say that my image is over here. And I want to know what type of mirror has produced that image. What kind of mirror, convex, flat, or concave, has produced this image? The image, this is the image right here. This is the image. This is the object. And what kind of mirror produced that? All right, I'll stop at 50 seconds. 50. Okay, C is right. It's a concave. This is like the magnifying mirror, right? I know it's not convex. How do I know it's not convex? Because convex, they also produce virtual images. But how do I know this isn't a convex mirror? The image in a convex is smaller. So here my image is bigger, so it can only be a concave. If this was a smaller image, it would be a convex. If the image was the same size as the object, it would be a what? It would be a flat mirror. If the image was over here, it could only be a concave mirror, and the image would have to be inverted. Concave mirrors are the only mirrors that produce real images. All right, let's go on now to, oh wait, let's see. Which of these mirrors will produce a virtual image under particular conditions? The concave, the convex, or the flat? Not that they always produce a virtual image, but they're capable of producing virtual images. Which of these is it? Sorry, I'll stop here in just a second. All right, I'll go to 115. 115. All right, good. A is the right answer. They can all produce virtual images. A convex and a flat always produce virtual images, and a concave can produce virtual images when the object is inside the focal point. So A is the right answer. Okay, so let's see. Let's do a few clicker questions. All right, so an observer at point O observes a light source S. Where does he perceive the mirror image of the source to be located? Where is the source, the image of S, as observed by this person here? See the image. See it at A, see it at B, see it at C, or see it at D? The image of the light source S. Stop at 45, 45, 5 more seconds. Very good, B is right. Remember, the object distance is always equal to the image distance. They're always directly across from one another. So uh, if this is my P, this is going to be my Q. It'll be directly across from it in a flat mirror. Did y'all try that, by the way, when you went home? Nobody tried it, did you? Nobody? Huh? You can try it this afternoon. If the observer starts moving towards the mirror, nothing happens, right? The image always stays where it is. It doesn't move around. Uh, this is more of a novelty, but I'll give it as a quick refresh. I'm going to tell you though. Actually, no, I'm sorry. We're going to skip this one. Just, no, so let's do this one as a novelty. So does this depend on your distance from the mirror? Um, you can try this when you go home, but the question is, if you move further away from a mirror, can you see more of yourself? You think? No, you can't, in fact. You try it when you go home. Look in your bathroom mirror and say, okay, I see from my head to my sternum or whatever. I see from here to here. And then try backing away. And you will still see the same amount. Now, if you lean in towards the mirror and sort of change your angle that you're looking at the mirror, it will change sort of what you see. But if you back away from the mirror and you keep your head level and your eyes straight ahead, you'll still see the same amount. You won't see more of yourself. You'll still see the same amount of your body regardless of how far away you are from the mirror. Now, some of you have vanities in your bathroom, is that right? Yeah, so if you back up, you can see your feet in your mirror, right? In your our bathroom is like 10 square feet, so we can't really back up at all in our bathroom. But if you have a vanity, then that's just blocking your view. But try this when you go home. Go in your mirror and then just back up from it and see if you can see more of yourself. You will not be able to see more of yourself. So the answer to this question is, does it depend on your distance from the mirror, is what? No. That you still see the same amount of yourself, whether you're up really close to the mirror or whether you're far away from the mirror. There's always somebody. All right. Let's see if I have a good joke for y'all. I haven't told y'all. You don't even get 90%. You have to get 90% for a joke. But let's see. There was a turtle or a snail went into the emergency room. He'd been in an accident, and the doctor asked, "Was like, man, what happened?" And the turtle said, "Well, I was in an accident with the snail said I was in an accident with a turtle." And I was like, "What happened?" He's like, "I don't know. It just all happened so fast." All right. Oh, I forgot about this. Sorry. Okay. I'm gonna skip this one to you. We get into the mirrors. So you want to set fire to a pile of dry leaves. Which of these mirrors is the best tool for you to use? The flat mirror, the concave mirror, or the convex mirror? All right, I'll stop at 28. Awesome. B is right. A concave mirror, because a concave mirror produces real images, and you can only burn stuff with real images. You're making a real image of the sun on these leaves or whatever it is they're trying to set on fire. An ant. You ever do this when you were kids? Set fire to ants? Right. Yeah, there was a Mythbusters episode too. Yeah. Y'all seen the Mythbusters episode where they try to burn the ship with Archimedes' mirror? He makes a big, big mirror out of little mirrors, right? Which is how they're making telescopes now, right? Um, but we'll see that. We're going to go outside in just a second. I'll show you that. By the way, one time, my son, he had a magnifying glass, and he's like, hey, let's set fire or something. So we went outside, and I was just curious. I'm like, gosh, I wonder how hot that is, really. And so I put my hand at the focal point, and it's really hot. It is very, very hot. Yes, it's quite hot. And it wasn't a very big lens. It was only about this big, but it was extremely hot. It hurt a lot. Okay, these folks are looking into a mirror. Based on the image, which of these is true about the mirror and the image? Now, you might not be able to see very well, but these are the people looking into the mirror, and then they see themselves upright and bigger inside the mirror. So what type of mirror is this, and what type of image is it? Is it a concave, convex, or flat, and real or virtual? All right, I'll stop at 40 seconds, 40, and then we're going to go outside, so go ahead and start putting your stuff away. Or you can come back in here, but. Okay, B is right. This is a concave mirror. It's concave. This is like when you look really close, like a magnifying mirror, you get real big. It's concave. It's an upright image. Upright images are always virtual. Concave mirrors are also converging mirrors. That means that light rays coming into them are going to converge at the focal point. And so we're going to go outside. It's a pretty sunny morning. We'll set fire to some stuff. So you can just go right out there, right through that door, and I'll meet you out there on the sidewalk.